Welcome to the 19th lecture on computational mathematics with SageMath. In the last lecture, we looked at how to find limit of a function and limit of sequences. Now, in this lecture, we will look at finding derivative of a function and some of the concepts related to that. So, let us get started. So, suppose you have a function f x is equal to log of x plus 3 into x cube plus cos 2x, and you want to find its derivative at x equal to 0. The way you begin with, you find the derivative using first principle, which is using the limit. So, if you want to find the derivative of f, then you find, if the derivative exists, you find the limit of f of x plus a minus f of a divided by x and as x goes to 0. So, this is what we will try to do. Since we have already found the limit, we have explored how to find the limit, we can make use of that. So, let us see. So, first let us define a, x and h as variables and declare the function f of x is equal to log x plus 2x cube plus cos 2x, and we want to find the limit the derivative of this function at x equal to a, which is 0, right. So, let us look at, if I take generic a and look at what will be the limit of this difference quotient f of a plus h minus f of a divided by h, and if that limit exists, then that will be the derivative. So, in this case the limit at x equal to a of this difference quotient f of a plus h minus f of a divided by h, as h goes to 0, is 6 a cube minus 4 a into cos a into sin a plus 2 divided by a. So, if you can cancel a, and then what you are left with is 6 a square minus 2 a cos a sin a, this will be cos sin 2 a. So, this will be a into sin 2 a plus 1 by a, and that is the derivative and at x equal to a. So, let us verify that using inbuilt function diff. So, if I say f dot diff and substitute the value of x as equal to a, then you will see that this is the derivative, which is same as limit of this difference quotient. Okay. So, generally we do not find derivative using this limit of difference quotient. We learn certain rules of derivatives, etc., and then we apply that to the sum of the derivative of standard functions. Okay. So, I am not going to get into verifying all these rules, etc., that is quite easy, you can verify. And so, let us look at a function f of x is equal to sine of cos 2x minus exponential of minus 1 x minus 1 the whole square. Suppose we want to plot graph of this function along with first two derivative, first derivative and second derivative. We already know how to find any kth order derivative using diff function. So, let us define this function f of x, and let us define f1 as derivative of f, which is equal to this, and let us define f2 as derivative of f, second derivative of f with respect to x, that is the f2. It looks very complicated, but it is able to find quite easily. Now, let us plot graph of both the functions, namely graph of f of x between minus 6 and 6, and so this is the plot graph of f of x, and we are giving the legend label to be f of x. Then P1 is the graph of f1 and the P2 is graph of f2, and then add P1 P plus P1 plus P2, and let me so that is the graph of f, which is the red in color, derivative which is green in color, and second derivative which is black in color. Now, you can even relate the behavior of derivative in terms of the various concepts that you would have learned about the function, similarly the second derivative, right. So, for example, if you look at this portion of the red curve, it is increasing. So, in that case, in this domain, the second derivative will be somewhat second derivative will be negative, right. So, let us look at, suppose you have a function f(x) is equal to x into sin 1 by x when x is non-zero and equal to 0 when x is 0, and the second one is x square into sin 1 by x when x is non-zero and equal to 0 when x equal to 0. So, if you look at these two functions, you must have seen that you can find the limit of these two functions and the limit at x equal to 0 exists, but how about the derivative? So, if I try to plot graph of both these functions side by side, so that is where we have used graphics array. If I plot graph of this function side by side, then this is how the graphs look like. This is graph of x into sin 1 by x, and this is graph of x square into sin 1 by x. So, in this case, if you look at this is somewhat very sharp turn here, sharp edge here in corner, I should say. In fact, you can draw a line y equal to mod x, and you will see that this near 0 the value is very close to that mod x function, which is not differentiable at x equal to 0. So, this function you expect this not to be differentiable at x equal to 0, whereas in this case this is somewhat actually close to y equal to x square from above and y equal to minus x square from below. So, this at x equal to 0 that and y equal to x square is a differentiable function. So, you can expect that this x square into sin 1 by x to be differentiable at 0, whereas x into sin 1 by x not differentiable at x equal to 0. Now, let us find out, if I want to check whether the limit of whether the derivative exists, I have to find out limit of the difference quotient. So, we want at x equal to 0. So, we have to say f of x minus f at 0 divided by x limit as x goes to 0. So, that and f of x 0 is 0, therefore, it is same as limit of f of x divided by x and x equal to 0. In this case, it says that it is defined, it is not defined, indefinite, right. Whereas, if I look at the second one, the second gx, limit of gx at by x at x equal to 0, this limit is 0. So, the derivative of g exists and it is equal to 0 at x equal to 0. So, graphically we are able to at least get some idea about whether the derivative should exist or not, and which we have verified. Okay. Now, let us look at, so you must have seen how this hyperbolic sine and cosine are defined. So, hyperbolic sine is defined by e to the power x minus e to the power minus x by 2, whereas cos x is defined as e to the power x plus e to the power minus x by 2. So, if you want to plot graph of sine hyperbolic and cos hyperbolic, one way to visualize this is we can plot graph of e to the power x and e to the power minus e to the power minus x by 2, and then add these two together, and then you will get graph of sine hyperbolic. So, if you look at this graph, this red is graph of e to the power x by 2, blue one is e to the power minus e to the power x minus x by 2, and when you add these two, the graph which you get is the graph of sine hyperbolic. So, that is how the graph of sine hyperbolic between minus 2 and 2 looks like. Similarly, you can do the same thing for cos x. So, let me plot this cos hyperbolic x. So, cos hyperbolic x, how do we do that? Plot the graph of e to the power x by 2, which is red in color, and graph of e to the power minus x by 2, which is blue and in color, and when you add these two, you get graph of cos hyperbolic x, which is black in color in this case. So, that is how you can visualize cos hyperbolic and sine hyperbolic, right. You can try with other trigonometrical hyperbolic functions. Now, many times your function is not defined explicitly, it is defined implicitly. So, that means y and x is satisfied by some equation, whereas y is a function of x. So, in that case you want to find derivative of y with respect to x, and how do we do that? So, let us take an example. Suppose you have this x and y defined by this equation, this implicit equation, that is 2 into x square plus y square to the whole square is equal to 25 x square minus y square, and here y is a function of x, therefore, you would like to find derivative of y with respect to x. The way you would have done is find derivative of this entire expression on the left hand side and right hand side, and wherever you have y, you write that differentiate with respect to x using chain rule. So you will get an expression in dy dx and you solve for dy dx. But Sage has inbuilt function to find the implicit derivative. But first let us plot graph of this curve which is represented by this equation, and we can use implicit plot. We have already seen how to use this. So if we plot graph of this function, this is how it looks like. It is a kind of infinity symbol. We also call this as figure 8. Now suppose at some point, so for example at x equal to 3, you can check that y will be plus 1 and minus 1. So 3 comma 1 and 3 comma minus 1 both are lies on this curve. Similarly minus 3 minus 1 minus 3 1 also lies on this curve. So suppose at that point we want to find the derivative and look at what is the geometric meaning of this. So let me find the derivative, implicit derivative, using a function called implicit underscore derivative of y with respect to x. So if you say, you have to say f dot implicit derivative y comma x. So that is how the derivative of y with respect to x looks like. So this you should try to, I am sure you can find out by hand also. Right. Now let us look at this point. Let me define the derivative at x equal to let us say 3 and 1 is equal to m. So that is the evaluate. In this you put x equal to 3 and y equal to 1, and then let us store that in m, and let us define a tangent passing through a comma b with slope m. So that is the tangent line or line passing through AB with slope m is what we are plotting. Now suppose we want to plot the curve along with this point and the line passing through 3 1 with slope m, and then see what it means. So therefore now you can see here this this I should say 4 comma 2 comma 4. Then you can see here this is the point 3 comma 1, and this line which we plotted, which is the line with slope m, which is the derivative of the function at this point, is a tangent to this curve. So therefore that is what the geometric meaning of the implicit derivative is when you find. So it is actually the slope of the derivative dy by dx at this point represents the slope of the tangent to this curve. Okay. If you try to change this instead of 3 1, if you say minus 3 and 1, and in this case now let me say it should be minus 4 comma 2. In that case you will get, yeah, this is the tangent at this point, minus 4 comma minus 2, let me put, right. Similarly you can explore this derivative at other points. Let us do one more example in this implicit derivative and see how we can explore SageMath. So you have a function, implicitly defined function this, and you want to find points at which the tangent is parallel to x axis. So first let us declare this function and plot graph of this curve. This graph of this curve looks like this. This is quite complicated one. So if I look at, for example, in this domain, the some points where the tangent is parallel to x axis, there will be several points. So what we will do is, first of all, let us find the derivative of y with respect to x using implicit derivative. So that is the implicit derivative. Now the slope will be parallel to x axis, the tangent will be parallel to x axis if slope is 0. That means numerator this function should be 0. So in particular numerator is 0. So you extract the numerator in NR by using dot numerator function, and then you find the zeros of this. This is a polynomial, so you will be able to find zeros of this. So it has actually two zeros. One is minus 1 by 3 into square root 3, which is same as 1 minus 1 by square root 3, and the other one is 1 plus 1 by square root 3. These are the 2 points. So, and if I look at the curve at 1 plus 1 by square root 3. So, this is some kind of vertical line and it will intersect around 4 points, similarly this side. So, it looks like there will be 8 points where the tangent is parallel to x axis. So, now how do we find out? So, we have found out the points x at which the derivative is going to be parallel to x axis. At these points you need to find out what is the value of y, right, value of y, right. So, you try to, so let us extract these points which we have found out, the points where x that slope is parallel to x axis. Let us store this in a and b, and let me say what are a and b. So, these are a and b. Now, we want to find substitute x equal to a in this expression. So, that I am calling as y, and then find roots of that y. So, that will give you there are 4 points in this case. You can see here there are 4 points, and these 4 points. So, x equal to a comma these 4 points are the points. Similarly, you can do by substituting x equal to b. So, there you get another 4 points. Now, all these 8 points. So, first let us make a list of these first 4 points for x equal to a, and the second one as points to the second for x equal to b, and then let us plot points of these first 4 points in red color and second points using point 3D in black color, and then let us add these 2 points to the curve. So, when we add to the curve these points, you will see here these are the 8 points at which the curve is the tangent is parallel to x axis. Of course, you could have also plotted the graph of this the tangent at these points. Okay, fine. Let us look at all of you must have studied this mean value theorem, which says that if you have a function f x defined on closed interval a b, which is continuous in closed interval a b and differentiable in open interval a b, then if you look, there is a point c strictly between a and b, that is in open interval a b, such that f dash at c is equal to f b minus f a upon b minus a. So, let us try to verify that for this function f x equal to x plus sine 2 pi x. So, how do we do that? So, let us define this function f of x, and a is equal to 0 and 2, a b is 0 and 2, and let us first plot graph of this function. So, this is the graph of this function, and end points are joined by this the chord. So, the geometric meaning of mean value theorem says this is called Lagrange mean value theorem, is that if you look at this chord, then there are points on this curve at which the tangent is parallel to this chord. So, in this case you can see that there will be some point here, there will be some point here, there will be some point here, there will be some point here. So, there will be 4 points in the strictly between a and b at which the tangent is parallel to this chord. So, that is the geometric meaning of. So, how do we do that? Let me again store m as the slope of this chord and find the points. So, if you look at this curve, this is the slope, and then you want to find out f dash x equal to m. M is the slope of this chord. So, that means you want to solve or find zeros of f x minus f dash x minus m. So, that is what is done. So, first root in this case, you can see here there is one root has to be between 0 and 0.5, that is actually 0.25. The second root, third root and fourth root, they are at 0.25, 0.75, 1.25 and 1.75, and at these points let us plot the tangent. So, let us plot the tangent. So, what will be the tangent? The tangent is L1 at C1 is L1 is equal to f of C1 plus F1 at C1, that is the value of the function at C1 into x minus C1, and then try to plot tangent to this curve. Let me show you, this is quite easy. This I do not require Sage here, but that is fine. Yeah. So, that is the geometric meaning of Lagrange mean value theorem. You could also apply to Rolle's theorem and then explore its geometric meaning. You could also, there is another mean value theorem known as Cauchy mean value theorem, that I'll leave this as an exercise, try to explore geometric meaning of Cauchy mean value theorem. Let us look at what is Taylor's theorem. So, I am sure most of you would remember, but just in case you do not remember, I am just stating the result. So, if you have a function f x defined on some interval I in R, which is n plus 1 times continuously differentiable, and then if you have any point inside this interval and look at any x in this interval, then you can write f of x is equal to T n x plus R n x, where T n x is actually nth degree polynomial, which is known as Taylor's polynomial, nth degree Taylor's polynomial, and R n we call as a remainder term, which is given by n plus 1th derivative of f at some point c strictly between a and b divided by n plus 1 factorial times x minus a to the power n plus 1. And this, how do we write this Taylor's nth degree polynomial? This is actually, this should be T n of x. So, T n of x is f of a plus f dash at a into x minus a plus f double dash at a divided by 2 factorial into x minus a whole square plus dot 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 n plus nth derivative of f at a divided by n factorial into x minus a to the power n. That is called nth degree Taylor's polynomial, and the function is actually approximated by nth degree polynomial with remainder. And in case you have higher derivative, one can show that this remainder goes to 0 as n increases, right. So, this is actually a basis for all these numerical evaluation of function. For example, when you want to find out sine of something, cos of something, exponential of something, actually it uses this expansion depending upon the accuracy and gives you the value. So, that is the very important concept which is kind of used for approximating the value of the function. Now, let us take an example. Suppose I have function f of x is equal to x into e to the power minus x square by 2 plus sine 3x, and suppose we want to find out 5th degree Taylor's polynomial of f with about x equal to 0. So, here a is equal to 0, n is equal to 5, and then I am defining that Taylor's polynomial is T n x f dot Taylor with respect to variable x and at the point a, and the degree is n. So, let us ask it to show what this is the Taylor's 5th order Taylor's polynomial. If I say instead of 5th, if I say 10, this will give me 10th degree Taylor's polynomial, right. So, that is how you can find Taylor's polynomial or Taylor's approximation of any function. Now, let us try to plot graph of this function along with the Taylor's polynomial. Let us say we want to plot graph of first order Taylor's polynomial. First order Taylor's polynomial will be nothing but the tangent. So, it is the linear approximation. So, let us try to plot its graph. So, you have graph of this function and we are plotting Taylor's polynomial approximating the function about x equal to 0 and first order. So, that is the tangent. If I increase n to 2, this will be quadratic Taylor's polynomial. Okay, I think yeah. If I increase to 3, then that is the actually in this case third order Taylor's polynomial is very quadratic. The third degree term will be missing. Oh, okay. So, this is I have to say here n, yeah, and increase this to 3, right. And if I increase it to let us say 5, this is the 5th, and you can see here this green this red color, which is the graph of the Taylor's polynomial, is very close to this actual function. So, that is what I meant by saying as you increase the degree, the function will be very close to the actual the polynomial T n, that is nth degree Taylor's polynomial, will be close to this the actual value of the function. So, you can even create animation for this. Let me just leave you this code using Sage Interact, which will kind of create an animation where you can vary the points and also plot the various Taylor's polynomial and other things. So, you can explore this, you can run this in Jupyter Notebook. Okay. At the end, let me leave you with a few exercises. So, these are some of the exercises. The first exercise is to find the first derivative of this function and plot its graph along with the graph of the function, and for various values of n you find the derivative of x to the power x. Then the third one is look at this function, find first 4 derivatives, then you look at this implicitly defined function, find first derivative and second derivative, and then the third problem is to verify Lagrange mean value theorem for this function, and the fourth problem is find Taylor's approximation to e to the power minus x square into cos 2x and plot its graph along with the Taylor's polynomial of degree 1, 2, 3, 6, 7, 9, 10. So, this is just to demonstrate the approximation of the function using Taylor's polynomial. Okay. You can even tabulate the error term and you can create a Sage Interact, which code I have already given you. Okay. So, these are the some exercises, all these exercises are there. So, you can try to solve them, they are quite simple. So, next time we will look at some more applications of derivative using SageMath. So, thank you very much.